So last time we were discussing various applications that lead to systems of linear algebraic equations. So that's what we looked at last time. So we've been overall reviewing vector matrix algebra, but reminding ourselves that this is something that is of interest to us as engineers, not just because math is fun for the sake of math, but because this is useful to us as engineers. So we did some definitions, vectors and matrices, and then algebraic operations, talk about dot products, cross products, matrix multiplication, things like that. And what we're going to look at today is how we actually solve these systems of equations using exact methods. These are methods that you probably have seen in some form before, so we'll just review them. And then we're going to start talking about mathematical software, how we're actually going to do these operations on our computers throughout this class. And I've kind of been hinting at all that through discussion on the syllabus and earlier in the class. And so we'll kind of bring that home, make it more concrete today. All right, so we're trying to solve these linear systems of algebraic equations. They pop up various places. Remember the applications we did last time, and these are just a few of the many, many situations. So we had a circuits example, parallel circuits example. We had two static systems. One was spring masses, one was a truss. And then finally, a little bit more involved, we looked at a numerical method applied to a simple fluid mechanics problem. In all of those cases, and again, in many, many more, they end up, when we ask the physical question, what is the solution for this physical problem? They end up being mathematically, you need to solve this system of linear algebraic equations. So that's where this has all been kind of coming to a head. So we're going to talk again today about exact approaches, the kind of ways that we would use by hand for smallish systems. And then in chapter 3, we'll talk about how this is done using numerical methods and using mathematical software for much larger systems, which we, of course, care about as engineers. So just to kind of lay the groundwork, we've gotten a sense for what a system of equations is from our applications, but let's be even more specific. So the first question I want to make sure we're clear on is, why are these linear equations? So a linear equation only involves constants and x's. Actually, that should be a u. Sorry, it should be a u. So only constants and u's. There are no u squareds. There's no sine u's. There's nothing of the sort. Only constants and u's. So it's a straight line. If you were to plot it, it would be a straight line. Y is equal to mx plus b. So for a single equation involving n variables, it would look like this. It would be a constant times u1 plus a constant times u2, all the way up to n. N is equal to some known constant. So we know the a's and we know the b, and then the u's are the variables. In 3 dimensions, we would use x, y, and z. In n dimensions, we'll use u1, u2, u3, u4, u5, up to un. So that's one linear equation. Now what we have are systems of equations. So we have, in this case, m. M is the first index, the first subscript, which indicates the row or the equation number. So this is the first equation, second equation, third, fourth, and then this is the mth equation. And they are all equations of 1, 2, up to n variables. So this is m, Mary, equations for n, Nancy, variables. And then again, we have the right-hand sides, the b's. So in general, what we know are all the a coefficients and the b constants on the right-hand side. And what we're looking for are the u's. We're looking for the values of u's. So the values of u's would be the forces in the truss members. That would be the currents in our parallel electric circuit. That would be the velocities at the discrete points in our grid for the fluid mechanics problem. Those are the dependent variables that we're looking for. In matrix form, we write it as a u is equal to b, where the b is all the B constants on the right-hand side as a vector. The U is a vector of all the values that we're looking for, the U's that we're looking for. And then the coefficient matrix A, which is M by N, so M rows by N columns, that is all the coefficients A11, A12, A13, all the way through. Now you notice this is a matrix multiplication problem. We have an M by N coefficient matrix. The solution vector is N by 1. So notice that the inner dimensions are the same, and the result is the outer dimension, so it's M by 1. So B is M by 1. So all the matrix multiplications rules apply and everything's fine. Now the way to look at this is this first row corresponds to the first equation. So these constants, A11, A12, and so on, and then the B1, those are all the constants in the first equation. So the first equation is A11 times U1 plus A1 times U2 plus A13 times U3, all the way to A1N times UN is equal to B1. That's the first equation. Second equation is the second row of A and the second row of B. Third row, third, all the way down to the mth row. So when you look at it written out in equation form like this versus matrix form like this, you can see the parallels, you can see the connection between them. And the numbering system, again, the first subscript indicates the row, the second subscript indicates the column. And that's why it was done that way in this notation here. All right, so we have this big AU equals B problem that we want to solve. Couple comments about this. In some cases, the B will be 0. And mathematicians always have fancy terms for things. So they say the system is homogeneous. Whenever you hear a mathematician say something is homogeneous, that means that something is 0. So in this case, the system of equations is homogeneous. That means it equals, all the equations equal 0. So the B is 0. So you'll hear that terminology sometimes. Now, in general, this solution is going to be the values of U that satisfy this system of equations, AU equals B. Normally, for our problems, we will have N equations for N unknowns. We have the same number of equations as unknowns, so we can get a unique solution, but that's not always the case. So you'll see situations where, in fact, the truss example, we had what, I think 10 equations for 7 unknowns, and we discussed the reason for that. But in any case, what we're looking for are the values of U for which all of these equations are satisfied simultaneously. So let's think about that in a simpler situation. So let's just take 2 equations. So something times x plus something times y is equal to b, something times x plus something times y is equal to b. So just 2 equations for 2 unknowns, just so we can picture it in 2 dimensions. Think of it as, again, x and y. So there are 3 possibilities. The first possibility is that these 2 lines are parallel. If they're parallel, they never intersect, and there is no x or y that satisfies both equations, so there is no solution. We say the system is inconsistent. It's inconsistent with having a solution. The second and more likely scenario for us is that the 2 equations are 2 lines and they intersect at a point. That intersection point is the value of x and y that satisfies both equations. You plot one equation, you plot the other equation, where they intersect, that is the xy value that satisfies both equations. In that situation, we have one unique solution corresponding to that intersection point. The third possibility is they could actually be the same line. So we write down the first line, we write down the second line, and they may actually be the same line. It doesn't happen very often, but it could happen. And in that case, the intersection points are, well, the whole line. So there's an infinity of solutions. So all 3 of these are mathematically possible. The second one is the one that we're typically looking for in physical problems. Not always, but almost always. So this carries over to systems of any size. You know, I can draw it with I can make it with my fingers for 2 dimensions, X and Y, but this carries over for any n. So any number of unknowns, any dimension. Now, there are various ways that we can use to solve the system of equations A equals B. I've listed 3 here. These are all direct methods that you have probably seen before at some point in your academic life. Gaussian elimination, matrix inverse, and Cramer's rule. So I'll just remind you how those work, and there's examples for each. So I'll go through this kind of quickly. You can look through the details, the examples, to really remind yourself and get some practice with this. Before we do that, we need to remind ourselves of determinants. So a determinant comes out of trying to solve these systems. So let me return to this 2 by 2 case. So we have 2 lines in 2 dimensions. So 2 equations with 2 unknowns. So let's just think about how we might try to solve that. Because there's only 2 unknowns, U1 and U2, we can just do some algebra, some simple algebra, and get expressions, general expressions for the solution U1 and U2. So let's just do that. It won't work for higher dimensions, but in the 2-dimensional case, let's do that and see what happens. So if I look at these and I say, well, to get an equation for U1, I have to eliminate the U2. I have to get rid of these U2s. So to do that, to get rid of the U2s, let me multiply the first equation by A22 and the second equation by A12, and then subtract them. And doing that, this term will cancel. These terms will cancel, and I just have an expression that I can solve for U1. When I do that, just a simple algebra, I get this expression here. I don't really care about this expression, but I'm highlighting in blue the denominator for a reason that you'll see in a second. So that's U1. If I want to do the same thing to get U2, then I need to eliminate the U1 terms. So I multiply the first equation by A21, the second equation by A11, subtract them again, and then I get this expression for U2. Again, I don't really care about the details, but look at the denominators in both cases. The denominators are exactly the same. So that denominator is called the determinant. So it's a special number that characterizes the coefficient matrix A. It only involves A. There are no B's in the denominator. It's the same for all the U's. And this is 2D, but if it was n-dimensional, it'd be the same thing. That determinant would show up in the denominator. So apparently it's some special number that shows up all over the place when you're trying to solve systems of equations. And indeed it is. And let me come back to this in a second. What it tells you is what to expect when you try to solve the system of equations. So it's really a diagnostic. We usually don't care about the determinant itself. I don't really care what the number is, what its value is, but we use it as a diagnostic. If the determinant, and this is how we denote it, we have the A in these vertical brackets. If the determinant is equal to 0, exactly equal to 0, we say that the matrix A is singular. Usually when you hear the mathematical term singular, that's usually bad. It means it's not invertible and there's no solution to the system of equations AU equals B. If the determinant is non-zero, then A is non-singular and it is invertible. And therefore you can get a unique solution. So this is the case that we're looking for in most situations involving solving systems of linear algebraic equations. Again, not always, but almost always. So the determinant is that diagnostic. Look what happens here. If the determinant was 0, well, you'd be dividing by zeros. So U1 and U2 would be undefined because you can't divide by 0. All right, let me come back and remind us how to get determinants of first 2 by 2 matrices. So you see it here. That's the expression A11, A22 minus A12, A21. And notice where it comes from. If I write down the 2 by 2 matrix A, Then I take the product of the diagonal elements, A11, A22, that's here, and then subtract off the product of the off diagonal elements, A12, A21, right here. So it's like this diagonal multiplication, plus the product of these two minus the product of these two. And that gives you the determinant. Same idea for 3 by 3. So here's 3 by 3, three rows, 3 columns. So the way you do this is you do the product of these, A11 times A22 times A33. That's the first term here, plus A12 times A23 times A31. That's the second. Plus A13 times A21, A32. That's the third. Boy, I sure want to do this on a computer in the future. And then you do the same thing, but from northeast to southwest, and you subtract them off. So minus A13 times A22 times A31, minus A12, A21 times A33, minus A11, A23, A32. And that's what these terms are. But it just gives you a number. You just get a number. So for 2 by 2, 3 by 3, it's easy to do that diagonal multiplication. You can just do it quickly on a calculator, and that gives you the determinant. For larger matrices, this diagonal multiplication process doesn't work. So you definitely don't want to do it by hand. If it's 4 by 4 or larger, you want to use MATLAB, Python, or something else. You don't want to do this by hand. 2 by 2, 3 by 3, doing it by hand is not that difficult. Okay, so let's look at then our 3 exact methods for solving systems of linear algebraic equations, primarily the way we would do it by hand, not on a computer, but by hand. These are not, they're either not easy to program or they're not efficient to program, but they're easy to do for small systems of equations by hand. So Gaussian elimination, it's named after Gauss. Gauss elimination is a very simple idea. It's kind of a complicated string of operations, but it's a very simple idea. The idea is as follows. We can do to our system of equations, A equals B, we can do what are called elementary row operations, which are things that do not change the solution to the system of equations. They just change the system of equations, if that makes sense. So I'm going to change the coefficients in my system of equations by doing these various elementary row operations. But in doing so, none of them change the actual solution. So I'm going to take my A u equals B, and I'm going to do these operations over and over again until I get a system that's easier to get the solution from. So that's the idea, and it's obvious when you see it played out. There are 3 elementary row operations. The way to think about these are the things that you can do to a set of equations, but that don't change the solution. So obviously you can interchange the order of the equations. That's fine. So I'm posing this as what you do to the equations that corresponds to the rows in the A u equals B matrix. So you can interchange rows in the matrix. I can swap row 2 and 3 if I'd like. And that doesn't change the solution because that's just equivalent to swapping the second and third equation. I can also multiply an equation by some non-zero number. If I multiply the left side and the right side by some number, I haven't changed the equation. I've just made it look a little different. So same idea with the row. I can multiply through a whole row by some number. Third, I can add, or by extension subtract, I could add a multiple of one equation to another. So I could take the second row, multiply it by something, and add it to the first row, for example. That will change the coefficients in the system of equations and in the matrix, but it won't change the solution of the system. So the step-by-step procedure is as follows. And again, you probably have seen this before at some point in your academic lives. It's harder to explain it than it is actually to do it. Doing it is tedious. I almost always make a mistake the first time. I almost never get it right because there's so many little calculations that you're doing. And so I almost never get it right the first time, so it is tedious and painful, but it's simple in the sense that the steps are quite simple. So the first step is to write down what's called the augmented matrix. So that's just the A augmented with B. You literally just slap the B on the right side of A. It has the same number of elements as there are rows in A. So normally the way we do that is we put a line here between them to indicate what's to the left is the coefficient matrix, what's to the right is the right-hand side vector. But basically then, everything that has to do with the first equation is in the first row. Everything that has to do with the second equation is in the second row. And therefore I can do these operations. I can multiply through, I can swap, I can multiply and add, whatever. And I just do it to the entire row, but now including the B. So that's the augmented matrix A with B. Then we want to, let me show you what we want it to look like in the end. Now let me look at this example. The way we want it to look in the end is I want to have leading ones in every row along the main diagonal like this. Everything below, I want to be 0. Everything above, I don't care. So that's called row echelon form. Row echelon form. So every row has a leading 1, and each row, the 1 is at least 1 step over from the equation above. The reason why I want it in this form is because now look what I can do. So that's called, the process of getting to this point, the row echelon form, that's called forward elimination. Again, I'll show you how to do that. We'll go through the steps. And then look what I can do. I can do what's called back substitution, because this last equation says that 0 times u1 plus 0 times u2 plus 1 times u3 is simply 1. So that says u3 is 1. If I know u3, then I can back substitute that result into the second equation, which says that u0 times u1 plus 1 times u2 plus 2 times u3 is equal to 3. But I already know what u3 is. So I can now solve for u2. And then from u2 and u3, I can now solve for u1. So we're doing back substitution, getting the solution for u3, back substituting to get u2, back substituting to get u3. Okay, so that's why we want to get it in that row echelon form. Okay, so here's how we do it. So the first step is we want to get rows with leading zeros, just move them to the bottom. Because again, I want this 1, 1, 1 down the main diagonal. So I don't want any ones where they're not, any zeros where I want a 1. So just swap the equations so that the leading zeros are at the bottom. That'll just make our lives a little bit easier. Then you divide through the first row by a11. So that's the coefficient in the 1, 1 slot of your A matrix. So I'm going to call this A12 prime, prime, A1n prime, B1 prime. So that just means it's now been changed from its original value because I've divided through by A11. What that does is it gives me this 1 in the 1, 1 slot. So boom, the first equation is done. The first equation is that the first row is in the form I want it. It has a leading 1 in the first position. Makes me happy. Okay, now what I want to do is I want to zero out all of the elements below that leading 1. So to do that, I will take and use the first equation and do some multiplication, addition, or subtraction to make this A21 be 0. So here's how it works. For this second row, to turn this element into a 0, I take the A21 and I multiply it times the first equation, and I subtract. Because that makes, by multiplying by A21, I now have an A21 here and an A21 here. So when I subtract them, I get a 0. Now, obviously, I have to do that all the way across, and that's the tedious part of this. So I do it all the way across, multiply, and then add or subtract another row. but that gives me now a 0 in the second column, second row, first column. Then I do the same thing for the third row, fourth row, fifth row, all the way down to the nth row. And that's going to change every single one of these values in the rest of the matrix. But you can see now the first column is done and the first row is done. So I can just leave those, I'll use them, but I'm not going to change them ever again. And now I look at what's left and I do the same thing. I now want to make this element a 1, the A22 prime. I want to make that a 1. So I divide through by A22 prime, this equation. That makes this a 1. And then I use that equation to eliminate all of the elements beneath it. And then the second row is done and the second column is done. And I just keep doing that on smaller and smaller and smaller submatrices until I get to that row echelon form that I talked about. 1s down the main diagonal and all 0s below. Then I can do the back substitution that I mentioned. So the last equation, the nth equation, now only has one unknown on the left-hand side, so I can just solve for it. The second to last equation only has 2 unknowns, but one of those I now know, so I can solve for the other unknown. You just back substitute, back substitute, back substitute, all the way up, and you get all the values of U. Okay, so here's an example. I won't go through it because it's kind of boring, but it's good practice. So if you haven't done this for a while, just go through it and it'll remind you the details, the steps. If you have done this for a while, then disregard the solution and try it and see if you get the same answer. There are some slight variations on the steps as I gave them. So if you have a different way of doing it, that's perfectly fine. The end result is the same. The end result is going to be the same. So if what I'm doing is confusing, you're saying, well, I don't do it quite that way. I always multiply by a negative and add instead of multiply by a positive and subtract or whatever. That's fine. As long as you get the same answer. So anyway, this is just walking through the steps, and it shows that in the end, you get the solution 1, 1, 1. All right, so it shows the forward elimination and the back substitution steps. So you can go through that. The second approach, common approach to solving these is matrix inverse. The good thing about Gaussian elimination, it is rather tedious, but it will always work. So even for our truss example, where we had 10 equations and 7 unknowns, if you did Gauss elimination on that system of equations, you will get the right answer. And if there is no answer, then Gauss elimination will tell you that there's no answer. If there's an infinity of solutions, Gauss elimination will tell you that there's an infinity of solutions. So Gauss elimination always works. It's not always the easiest. It's not always the most efficient. It's not always the best approach for any given system, but it will always, always work for any situation. Matrix inverse, on the other hand, only works when you have an invertible matrix A. It has to be invertible to have an inverse. So first of all, it has to be square, and then it has to be such that the determinant is not equal to 0 for the reasons that we said a moment ago. So for invertible A, we can do the matrix inverse. And then it's really simple. You just start with A, U equals B. You pre-multiply both sides with the inverse of A. So then I have the inverse of A times U on the left is equal to the inverse of A times B on the right. Now, the inverse of A times A, by definition, that's just the identity matrix. So it's not, but it's kind of like canceling the A by dividing by A. There is no matrix division, but this is the generalization of it. So you multiply by the inverse, A inverse times A is I. So now on the left-hand side, I just have U, which is what I'm looking for. That's the solution I'm looking for. And on the right-hand side, I have the inverse of A times B. So again, it's kind of like if I had just a simple equation, scalar equation, A times U is equal to B. I divide both sides by A, and I have U is equal to B over A. So this is kind of like the matrix equivalent of that. U is equal to the inverse of A times B. Now, one of the nice things about the inverse approach is the hard work in solving a system like this is getting the inverse, as you'll see. Once you have the inverse, all you have to do is do the inverse of A times B. That's very straightforward. It's just a matrix vector multiplication. So if you have situations where B changes, but A does not, then this is great. Now, where did that come up on Tuesday? Well, remember our truss problem. So we're thinking about what information went into A, what information went into B. The information that went into A was the geometry of the truss. So if I keep the same geometry of the truss, and only change the external loads, which went into B, then this is perfect, because I don't have to redo the inverse of A. I just change the B, redo the multiplication, and we're good to go. Notice what happens if B is 0, in which case we have a homogeneous system of equations. If the system is homogeneous and B is 0, we're multiplying the inverse of A times the 0 vector. Well, guess what that is? That's 0. We call that the trivial solution. Again, mathematicians love to have silly names for 0. So if you have an equation that's equal to 0, we say, oh, the equation is homogeneous. If the solution is 0, we don't say the solution is 0, we say it's the trivial solution, which is 0. Okay, so everything makes sense from a mathematical point of view. Now, how do you get the inverse? One way to get the inverse is to use Gaussian elimination. And the reason why this works is the operations that take A and change it to I, change I to the inverse of A. So what you do is you take your matrix, your n by n matrix A, you augment it with an identity matrix of the same size, n by n, and you look at the left-hand side and you do the row operations that convert that into I. Now, I, if you were to do that, that's called the reduced row echelon form. So row echelon form is ones down the diagonal and zeros below. Reduced row echelon form is ones down the diagonal, zeros below and above, which is the identity matrix. So for solving systems of equations, that's not necessary because we just do back substitution, which is easier than doing the extra elementary row operations to get all the zeros above. But anyway, so this is one way, and often the best way, to get an inverse if you're doing it by hand. So for the same system of equations as we had in the last example, which was solved using Gaussian elimination, what we do is, in order to get this inverse, you simply augment it with the identity matrix. So this is the same A as before, but rather than augmenting it with B, you augment it with I, the 3x3 identity matrix. You do the same elementary row operations as before. It's just that now, rather than the B coming along for the ride, it's this identity matrix that's coming along for the ride. So whenever you multiply through by some number, you have to make sure you do it on the right as well, all the way through. So when you do those same steps, and you can check this, when you do the same steps in the same order as before, this is the row echelon form that we got. This is not the inverse yet because I still have to zero these out. This one's already happens to be 0, but in general, I'd have to zero all of these out. So I'm not quite at the inverse yet, but this is just after having done the same steps on the same matrix, this is where I'm at, kind of in the middle. So now I need to zero this one, and I need to zero this one. So that's what these two bullet points are doing. Okay, so I can use this equation to make this a 0. I can use this equation to zero this one. Same idea. So making the zeros above is just like making the zeros below. Multiply through by a number, and add and subtract, add or subtract the appropriate row. When you do that, you now end up with this. On the left is indeed the 3 by 3 identity matrix. And now on the right, you have the inverse. So the inverse of A, you can see these 9s, I pulled them all out. So 1/9 times this 3 by 3 matrix, that's now the matrix inverse. When I multiply the matrix inverse times B, here's B, 3, 3, 3, I get 1/9 times 9, 9, 9, which is 1, 1, 1. Same solution. So which one is more work? For this case, for the 3 by 3 case here, probably getting the inverse is a little more work because you're doing the Gauss elimination on a 3 by 4 matrix rather than, sorry, you're doing the Gauss elimination on a 3 by 6 matrix rather than a 3 by 4. So it's a little bit more work in this particular situation. But of course, you get the right answer. Then there's Cramer's rule. I'm not going to spend much time on Cramer's rule. We engineers love Cramer's rule, and they teach us Cramer's rule because it's very simple to execute. The problem is it only works for up to 3 by 3. Anything larger than 3 by 3, Cramer's rule doesn't work. Remember how it goes. You take for U1, U2, U3, UN, they're all divided by the determinant of A, which makes sense because remember that's where the determinant comes from. But in the numerator of each one is a slightly revised determinant of a slightly revised matrix. What you do is you take the right-hand side vector B and you replace the first column of A. So that gives you A1. Take that determinant, divide by the determinant of A, you get U1, and you're done. And because it's so easy to do determinants of 3 by 3 matrices, this is super simple. It's really easy to do, and you'll see the example in a second. Then for the second one, you take the second column of A, replace it by B, find that determinant, divide by the determinant of A, and you get U2. So we love this technique because it's super simple. It's just a whole bunch of easy determinants doing the diagonal multiplication. Once again, however, it does not work. It does work. I shouldn't say that. It does work for larger matrices, but it's very inefficient because the diagonal multiplication does not apply. So you have to use what are called cofactor expansions, and they get really messy. And so for larger than 3 by 3, effectively, Cramer's rule is not worth even considering as an option. So for larger matrices, you would use Gauss elimination. All right, so Cramer's rule is basically useless, but here it is. Just to remind you, we'll never see it again for the rest of the semester, probably. But just to remind you, so here's the same 3 by 3 system of equations, and here are the 3 determinants that you do, boom, 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 and you get the same solution, 1, 1, 1. Okay, so Gauss elimination is kind of the standard. That's the starting point. Again, it's not always the best, it's not always the easiest, but it is the point of comparison for all the other methods that we're going to look at. You would never want to do by hand the Gauss elimination on a 10 by 10, 20 by 20, 100 by 100, 1,000 by 1,000, million by a million matrix. Of course, you would never want to do that. You would have it solved on a computer, first of all, and if you're going to have it solved on a computer, there are more efficient ways for the computer to do it. If I'm doing it, I want a method that's easy to remember and relatively straightforward to apply. If I'm going to have a computer do it, computers don't care. They have no emotions. So if I have a computer do it, I'd rather have it done using a very efficient technique so I can get it fast for very large matrices, even if that requires doing a lot of tedious calculations that I would never want to do. So that's the beauty of a computer, is they're dumb, they have no emotions, and they just love doing the same thing over and over and over again. So we'll take advantage of that when we look at how to solve these on a computer. Okay, any questions about that? So we won't be doing a lot of Gauss elimination or finding inverses, and very little, if any, Cramer's rule. Maybe I'll give you one on a homework assignment or something just for fun, because they're only useful for small systems by hand. That's fine for our academic careers up until this point, but going forward, we're going to have larger systems of equations with more unknowns, and therefore we need more efficient and robust techniques, and that means using a computer. I don't want to have to do it. I'm too lazy. Any questions, comments, concerns, issues, complaints? Are we alive? Good. Mask emotion. And we teachers, we didn't realize how much we depend on your nonverbal feedback until COVID hit. And now we realize how, if you ever hear one of your instructors, one of your professors, and they're kind of repeating themselves, you think, well, didn't they just say that a few minutes ago? You know why they're doing that? It's a subconscious teacher thing. When I look around the room and I think, and I see a lot of weird blank stares, well, obviously they're not getting it. So let me try to explain it in a different way or whatever. So in the vacuum of no feedback, we start just repeating ourselves. So watch for that. It's kind of funny for the first few times, and it gets a little bit tedious after that, but nevertheless. All right. They're already masked. Your emotions were already masked. You did not need a physical mask. Vincent, we're gonna have to, I don't know, we're gonna have to work on that. We need you. We engineers, yes, we are nerdy and geeky, but that does not mean we don't have emotions. Do not mask your emotions. I am not a psychologist. That's as far as I'm gonna go with that. All right, any other questions on this then? Okay, good, because I don't want to talk about it anymore. It's boring. So let's talk about how we do these operations on a computer, because oh my goodness, it's gonna be so much easier and more fun to have our computer do these things than do it by hand. So what I'm gonna do is I'm gonna introduce the various tools we have in our engineering toolboxes for basically mathematical software for doing these things. So I'm gonna focus on MATLAB and Python. I've included material for Mathematica, but no one ever uses Mathematica for reasons I'll mention. I shouldn't say that. You guys aren't going to want to use Mathematica for reasons that I'll say. I love Mathematica. It's extremely powerful. It's very useful. But for your stage of life and the kinds of things you're focusing on, MATLAB and Python are really the better choices and more likely to be used in industry. So I'll focus on those two, but I'll briefly mention Mathematica. So I'll kind of introduce where they came from, their strengths and weaknesses, how you do these various linear algebra operations. You can see by comparison how they're done in these various platforms, and also kind of give you a sense for, or help you make the choice that's best for you. So again, I'm not prescribing one or the other, but I've kind of laid out the parameters, but this will be the time that you can really start thinking about, okay, what makes sense for me? You'll hear me talk a lot about Python, and that's because Python is the new kid on the block, newish kid on the block. It is clearly taking over the technical scientific computing world, and for good reason. So that's where things are going. And it's just a matter of, when do you want to get on that train? You want to get on that train now and use 350 as an opportunity to get off the MATLAB train and onto the Python train? Or do you want to delay that until the next stop or the next stop? That's up to you. All right, so let's start with MATLAB, because that's what's more familiar to most of you. It stands for Matrix Laboratory, which tells you exactly what its origins were. It started in the 1970s, and its origins were to manipulate vectors and matrices very efficiently on computers. So linear algebra is MATLAB's core strength. That's what it does best. It is based on LAPACK and BLAS. These are computing libraries. LAPACK stands for Linear Algebra Package. BLAS stands for Basic Linear Algebra. What's the S? Software? Systems? Subroutines. I think it actually stands for subroutines. I forget. So these are standard, very well established, excellent, very efficient libraries, functions that have already been written many years ago. They've been beat on, they've been tested, they work all the time, and you really can't improve on them. So most everyone, MATLAB included, builds their software on top of these. Now this is this is transparent to you. You will not see LAPACK, you will not see BLAS. It's one of the nice things about using MATLAB or Python or Mathematica. It's taking advantage of these libraries, but it's all under the hood. You don't have to worry about it from the user's point of view. There are many add-on packages. Some of you may have or will use Simulink, for example. And so there's lots of add-on packages like Simulink that you can add on to the basic MATLAB to add more functionality of use in science and engineering. It is very popular and remains so in engineering research and practice, so in industry. A lot of people use MATLAB both in the research and in industry. But I will say again, that is starting to shift towards Python, and again, for good reasons. It is proprietary and commercial. So it's developed by a company, sold by a company, MathWorks. They're trying to make money. It is available for all 3 major platforms, Windows, Mac OS, and Linux. But one of the reasons why, it's not the best reason, but one of the reasons why people are latching on to Python is because it's not associated with a particular company. If something were to happen to MathWorks, if someday MathWorks were bought out by Microsoft or some other company, who knows what would happen to MATLAB? Maybe it would just go away. So it's a little bit risky. Now, is that going to happen? Is it going to go away? Probably not, because there's so many people using it. But Python, you don't have to worry about. It's open source, it's free, and no one person can make the decision to put the kibosh on Python. And plus, did I say it's free? So it doesn't cost us, and we engineers, we're cheap. So it doesn't cost us any money. In terms of resources to learn MATLAB or to deepen your knowledge of MATLAB, in the syllabus, I had Galat and Subramaniam. So their book is a numerical methods book. So everything we're going to talk about in this class from a numerical methods point of view is in that book. That's actually not true. I lied. There's one topic that's not in the book. And it shows how to do all these things in a general context as well as in MATLAB. And there's an appendix on MATLAB itself. So it's a decent book. It's from a numerical methods book. I wouldn't say it's the best one, but if you're interested in doing MATLAB, numerical methods in MATLAB, it's a fairly good resource. You can also, of course, look at the MathWorks website. I have placed some M files on Blackboard. I'll be honest, they're old. I have not updated them because I don't use MATLAB on a regular basis. But if you are using MATLAB, everything that you need to be able to do is in there somewhere. So they're M files with lots of comments for documentation. So things like plotting, linear algebra manipulation, programming. So, for loops and if-then statements and those sorts of things. All of that is covered in a series of M files that you'll see on Blackboard if you're interested. There's, of course, also MATLAB help within the MATLAB software package, and you can access that directly. There are 2 ways to use MATLAB, and if you've used MATLAB to any degree, you probably have used both. One is simply through a command window. So you pull up the MATLAB program, and in that window on the right over here where you type your commands, you just start doing MATLAB-y stuff. So you put in a matrix, you put in a vector, you get the inverse of the matrix, you take the inverse times the vector, and you get the solution for you. That's fine for things that you're just going to do once. So it's like a glorified calculator. You punch the numbers in, you press the button that does the operation, it gives you the result. Fine, you're never going to do it again, or at least not. It's not involved enough to want to capture that. The typical way that we will use it, and this is what you do when you get more involved types of MATLAB operations and programming, is to use what are called M files. They're called M files because they're .m. It's not very creative, but they're just text files, script text files. You can type in any text editor. There is a text editor built into MATLAB. And so that's where you type your M files, boom, 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 boom. And then you run them over here and it shows the results. Plots pop up in separate windows, blah, blah, blah. So the 2 ways that in this class you would be using MATLAB will be either using built-in MATLAB functions, right? So if you want the inverse, there is a built-in inverse function. You just put in the matrix, say I and V of the matrix A, and it'll give you the result. So those are using built-in functions. So they're often calling BLAS and LAPACK and so forth. The other way to use it, which you will also do in this class, is to write your own programs. So this is like how we used to do it in the good old days, Fortran and C. So the point is, MATLAB, Python, the built-in functions don't always do everything you want it to. And so there are times when we'll need to write a program to do that ourselves. So they're longer, they're more in-depth, more detailed. We call those user-defined functions. So in the problem sets, I'll always make it clear. Should you do this by hand? Should you use built-in functions in MATLAB or Python? Or should you write a user-defined function? So those are the three possibilities. And that's the difference. Built-in function is using built-in functions. User-defined function is a function that you write to accomplish some task using some algorithm. So all the operators in terms of scalars, exactly what you'd expect. Plus, minus, multiplication, division. The asterisk is multiplication. It has built-in functions for all the usual math operations that you want, sines and cosines, square roots, exponentials, and logs, and so forth. Operations on vectors, which are 1D arrays. So this is something you're gonna have to get used to. In math, we talk about, and physics and engineering, we talk about scalars, vectors, and matrices. In linear algebra, in these software packages in programming, these are all arrays. So a vector is a one-dimensional array. It's an array with just one index. A matrix is a two-dimensional array. It's just an array with two indices. It's still rows and columns, so they're basically the same. It's just different terminology. So for a vector, which is a 1D array, you can add them, subtract them, you can take dot products and cross products of them. Very simple, straightforward. Matrices, which are 2D arrays, you can do matrix multiplication with the asterisk. You can do the transpose. There's a determinant, inverse, eigen problems, which we'll talk about later in the semester. You can also do element by element operations. For example, if I do this, A asterisk B, that's going to do matrix multiplication. If what I really want is just take A11 times B11 and put it in C11, then you put a dot. And then that tells it to do element by element multiplication. Does that make sense? So those are different. Now, you can do seemingly silly things from a mathematical point. You could say, what's cosine of a matrix? It turns out there is a linear algebra construct cosine of a matrix, but that's not of our concern. If you do cosine of a matrix A, what that's going to do is take the cosine of the first element, A11 element, put it there. A21, A31 is going to take the cosine of every element. So it's an element by element operation. So a lot of these other things that normally you wouldn't think of applying to a matrix, you can apply to a matrix or a vector. It'll just do it in an element by element fashion. A lot of times in numerical context, you'll hear that is called vectorization. So you're basically doing the same operation to a whole bunch of elements, like in a vector. Special constants, so when you want pi, don't type in 3.14159. What you want is pi to machine precision. You want the most accurate, most precise value of pi that your computer and MATLAB can give you. So use the built-in function. So you just type pi. I is the square root of -1. There's an infinity, INF. There's even NaN, which stands for not a number. If you ever see a not a number, that means the number is too big or too small to be represented on a computer. So either it blew up, which is the more common case, or the number became so small that it can't be represented. Remember, we talked about that 10 to the -16. So if something is smaller than that, then the computer can't recognize it. So it's just NaN. Mathematica, again, I'm not going to go into any detail about this at all. The reason why is because its forte is in math and science research. So I use it a lot because I do more theoretical type research. Its real strength is in doing symbolic mathematics, which is the same thing that you do on paper. Now, if you think about that, that's pretty amazing. Doing algebra, calculus, solving differential equations, exactly, not with approximations, exactly. It's pretty amazing. So I use it for that. That's its primary strength. You can use it for more traditional programming. It does have all the built-in functions for linear algebra and so forth. But because none of you will be using Mathematica, I'm not going to really spend any time on it. If you're interested in just kind of getting a sense for what it's like, there is a Mathematica tutorial on Blackboard, and you could just kind of go through it. You can compare it. I've done a lot of the same things in the Python tutorial as in the Mathematica tutorial, so you can see how similar and different they are in doing those sorts of things. One of the great things about Mathematica is the notebook interface, so which is one of the primary ways that people use it. So a notebook, this is kind of what one looks like. It contains everything. So you can have descriptive text. You can actually have a structure to the document. So you can have headings, subheadings, and it's all collapsible. So you can collapse down this, subsection. So you can have description. You can have the Mathematica code, so operations and commands. You can have the output. You can have plots. You can even put in equations, all in one document. It's very nice. MATLAB, as you know, you write your M file in one window, right? And then you run it in another window. And then when you run it, whenever a plot is produced, it creates a new window for every plot. So if it's a complicated M file and produces a dozen plots, well, now you have actually 13 outputs. You have the output from this window, the command window here. And then you have the 12 plots that have been thrown up randomly on your screen. And it's always frustrating. A student comes in and wants to show me one. And of course, they've got to find the one out of the 12 that they want to show me. And of course, there's no way to figure out which one it is. And so they're all embarrassed and so on. But anyway, so the notebook interface is really nice from that point of view. Okay, all the same operations and so forth, just different syntax. You'll notice Mathematica likes capital letters beginning internal built-in commands. It's just a syntax choice. Okay, let's talk about Python. This is where I'll spend most of my time, partly because it's the one that you'll be least familiar with. Also, as I said, it's the one that is going to be taking over the scientific STEM world. At least that's the way things are looking. So I'll spend a little bit more time on this. First of all, and this is important, Python comes from Monty Python, not the snake, which is kind of interesting because a lot of the terms that are used, so I'm going to mention anaconda. Well, of course, that's a snake. So people use it in the wrong way, even in a, in that. Okay, so anyway, it's Monty Python, just so we're clear on that. That's the most important thing you need to know about Python. It started as a scripting language. Actually, several decades ago, it started as a scripting language. The script is a very short and simple program. So normally when you think of programming, you think of writing an application, or now we call them apps, right? So it's an app for your phone. It's a Zoom app for your computer. They're long, there are thousands of lines of code. A script is very short. It's often just a handful of lines, and it's just to do something very simple. As an example, say I worked at, say, JPL, not GPL, JPL, yikes, I'm just so excited. So you work at JPL, and every morning you come into work, and you download all of these files from the probes that are probing our solar system, and they all have strange, unuseful names to the files, right? So you get thousands of these images, and you need to change the names so that all of your colleagues know, which probe it came from, what time of the day that the picture was taken, what was the orientation relative to the asteroid, or not the asteroid, the asteroid, or the planet, or the comet, or whatever it's taking pictures of, what's the orientation. So you want a meaningful file name. So you're going to change all the file names accordingly. We're not going to do it by hand, right? So you write a script. It reads in the current name, and reformats in a way that a human can read it. It's meaningful. And then it's done. 5 minutes before you're even done making your coffee, let alone sipping it, you've done it. So a script is something like that. It's just very simple, does one task. That's how Python started. There are many scripting languages, C Shell, Bash, on and on and on. There's dozens of these, particularly in Unix environments. There's dozens of these scripting languages. Why Python grew to become its own programming language, full-blown programming language, is a very interesting historical development, but it has, and suffice it to say, that's what it is now. It is now a full-blown high-level programming language on par with something like C++. My favorite example is we all use Dropbox, right? I use Dropbox every day. No, you don't use Dropbox. Oh, you guys Google Cloud. Dropbox is amazing. You know why it's so amazing? Because it is so darn simple. You just plop a file into the folder, the Dropbox folder on your computer, and it's immediately in the cloud and available on my iPad and anywhere else. Dropbox code, usually the simpler the application, the more code required to do that. And Dropbox is a perfect example. The Dropbox code is all written in Python. Almost all applications that you use on your phone or on your computer are at their core C++. C++ is what's used by almost all computer scientists in general computer programming settings, not specific to scientific computing, but in general programming context. So Python now is on par, and that's my favorite example. So why didn't Dropbox use C++? They could have, and some would argue they should have, but the point is they could develop a full-blown application fully in Python rather than C++. So point being, it is now currently a high-level programming language that is worth us as engineers looking at. I've looked at Python usually like every 5 or 6 years over the last 20 years. And until a few years ago, I'd take a look at it, kind of where's it at? Is it useful? Is it on par with the tools I'm using? And is it anyway better than the tools I'm currently using? And the answer was always no, 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 not even close, until just a few years ago, for reasons that will become clear later on. One of the big differences between Python and other computing environments is because it's open source, there's a large community of developers. So who's developing MATLAB? Well, it's a bunch of paid engineers and scientists and mathematicians and computer scientists working for MathWorks. So who decides what new features the next version of MATLAB was going to have? Some business person, and some, what the engineers and computer scientists can convince them. In Python, there are people all over the world developing tools for Python for free, just out of the goodness of their heart. It's the amazing thing about open source software. So there's all kinds of extensions and packages and libraries, and there's new ones every day. So whatever field you work in, chances are there are other people around the world that are developing Python packages and libraries and so forth that are going to help you make your life easier. It is now to the point where whether you're a scientist, an engineer, a statistician, you work in data science or scientific computing, which would be the closest term to what we're doing, Python has several numerous tools for you. If you're into the latest AI and neural network stuff, it's all there. It's all in Python, not in Python, but as extensions and packages available on top of Python. So it is increasingly being used throughout the research community, as well as also in industry, because the tools are so extensive and they're being developed and improved upon every single day. It's really a remarkable thing that's happening, very organic. It's available, obviously it's free, it's open source, so it's available for free on Windows, Mac, and Linux, so anybody can use it. You can even run it on your iPad if you want. Not necessarily the best way to run it, but you can. Because it's open source, it can be confusing. So for someone that just wants to learn, I don't even want to learn, I just want to use it. Now I have to learn it, but I just want to use these tools, right? So the easier you can make it for me to install the MATLAB, install the Python, and actually start using it, the better as an engineer. I love computing. I do CFD, computational fluid dynamics, that's my life. But I don't do the computing part for the sake of the computing. Computers are just a tool for me. The software is just a tool. So I write programs to accomplish physics, to learn about physics, not to write programs for the sake of programs. So that being said, it can be confusing because there are so many different ways to install Python, to use Python, and the tools that are available that go on top of the basic Python installation. It gets very confusing. So what you need is someone, guess who, to tell you as an engineer, this is how you should install Python so that you get all the pieces that you need. And this is how you should use Python so you have all the capability that you could ever want. And then that just scales away all the complexity and the confusion. Python is really an ecosystem. So it's better, so C++ you talk about as a programming language. Fortran is a programming language. There are people behind it. There are people that decide what are the features that are going to go into the next C++ version that comes out, Fortran version that comes out. This is an ecosystem. There's a whole host of people all over the world making decisions about what they're going to add to this ecosystem, how they're going to improve on pieces that are already in the ecosystem. So it's constantly evolving, which is a little scary at times, but it's also kind of exciting. Because if you look at something today and you say, well, this is helpful. I wish it could do this, this, and this as well. Chances are in 6 months, 9 months, or a year, it will, because someone else has the same issues and the same concerns and the same demands. So again, it's better to think of Python not so much as a programming language per se, but as a whole ecosystem. So again, I would suggest starting with my tutorial. It has everything as a starting point that you'll need for this class, as well as more that you won't use for this class. So that's a good starting point to kind of get a sense for what's it like, how do I install it, all the details are there, and how do I actually do things. And you're free to copy and paste from the tutorial all you want. So you can use the examples I have in the tutorial as the starting point for writing your own user-defined functions or doing whatever else you need. Once you get started, once you are told what's the best and easiest way to install it and use it, it's no more difficult to learn than MATLAB. The learning curve is no worse than MATLAB in that sense. It seems worse, again, because there are so many options, but once it's narrowed down for you, it's not bad. Resources that you'll find on Blackboard are links for Anaconda, and that's explained in the tutorial, but Anaconda is by far the easiest way to get Python, as well as all of the tools and packages and libraries that you would need as engineers. That's all you'll need for this class. You will never need to download anything else and add it into your Python installation. It's all included with Anaconda. Anaconda is also an application. It's called Anaconda Navigator that'll download, and that's how you access your Python. However you're going to do it, whether you're going to use Spider, I'll talk about in a moment, or Jupyter Notebooks, talk about in a moment. You just start the Anaconda Navigator application, and it comes up, and you select what you want. It starts up all the stuff in the background that you need, so it's very transparent to you. It's like opening MATLAB. You don't have to think about anything. So again, the Python tutorial, you'll notice the strange suffix, .ipynb. IPY stands for IPython, which is a notebook interface to Python, and NB stands for notebook. So this is what's called a Jupyter notebook, which I'll describe in a moment. So that's mentioned here. So a Python file is .py, that would be pi. Python file is .py. A Python Jupyter notebook, which is my preferred way to access and interface with Python, is an .ipynb file, Jupyter notebook. Again, there are different ways to use it. I'm going to mention 3. There are actually more, some of which are mentioned in the tutorial. Some people like to use PyCharm. I have not listed PyCharm. I don't personally recommend it. PyCharm is more for hardcore programmers. So it has lots of the hardcore programming tools that CS people would want to have. It's an interface that's more familiar to them. For us, I think there are better choices. You can always use the command window. I don't recommend it, but it's there. So you can pull up on a Mac, you just pull up a terminal in Unix and you can type Python. It'll open up the Python kernel and you can just start typing in commands. It's analogous to using the command window in MATLAB. Type in A, what's the inverse of A? There's the result. Great. More likely, you'll do one of these two options. Spider is an IDE. IDE stands for Interactive Development Environment. So MATLAB is an IDE. So basically it's an environment that allows you to interface with the software, in this case, the programming. So you can access the M files, you can tell it to pull in this M file, run the M file, and so on. Same thing in Python. In fact, Spider, if you really like working with MATLAB in terms of the way you interface with MATLAB, but you want to use Python, then Spider is a great option for you. It looks almost identical to MATLAB. You have your command window, you have your window over here where you type your Python, not M files, but .py files. So it looks very, very similar. If you like more the notebook interface approach, which is my preference, then you use Jupyter. The Python commands are all the same. What you actually type in terms of the Python is exactly the same. It's just how you do it, the environment within which you do it. So this notebook interface, just like a Mathematica notebook, you can have a structure to it with headings and subheadings. In fact, it basically just uses HTML. So when you see a web page and you see a bigger heading, a smaller heading, that's just dollar signs or hashtags or whatever you guys call them. This symbol in my lifetime has evolved. It used to be when someone drew that symbol, you thought, oh, that's the pound. Not like the British pound, but like a pound. No one ever thinks about it that way. And then it became a symbol for a number, right? So a number, boom, boom. Now, of course, it's a hashtag. So it's still a number to me. But anyway, that's fine. So anyway, you can include headings, text. You can even include LaTeX if you like to use LaTeX for math. You can embed LaTeX right in the Jupyter Notebook, which is amazing. It's beautiful. You can have your code. You can run your code and it will generate the output and put it right in your notebook, including plots. So if you run some code and it generates those 12 plots I mentioned, all the plots are right there in the one notebook. So this is really a great way to do problem sets because it's all in the same place. You can describe what you're going to do, you can do it, and you can show the results, and you can discuss the results all within your Jupyter Notebook. So it's a really very nice environment to work in as far as using Python, as far as presenting your work in Python, and so forth. Again, two ways you can use it. You can use the built-in commands. I mentioned here NumPy and SciPy. We'll talk about that a little bit later. Or you can write full-blown programs, just like in Fortran C or MATLAB M files, and write your user-defined functions. So in that sense, it's very similar to MATLAB. You have all the built-in functions, in fact, many more because of this whole entire ecosystem around Python. So just some particulars. So the usual scalar operations, plus, minus, multiplication, division, they're all the same. This is something you just have to get used to with Python. It's not, don't think of it as an annoyance. It's just the way it is. Python itself, just Python, is this scripting language. So how people add to it is they don't change Python. They layer on top of Python all of these other packages and functions. So if you want to do stuff with math, there's no square root built into Python. there's no exponential or log built into Python. So someone had to sit down and write. So they wrote a package called math. So when you're doing Python, you have to import the math package. And then you have access to all these math functions: sine, cosine, square root, exponentials, just like anything else. And the package, then you have the name of the package dot the function that you want. And you can abbreviate these. So a lot of people will say import math as M. And then instead of typing math.cosine, you just type m.cosine, m.sine. Same thing with NumPy, which is numerical Python. Most people say import NumPy as NP. So rather than typing out NumPy every time I want to use, say, a dot product or a cross product, then I just type NP dot dot, NP dot cross. And you get used to it, and it's second nature to you. And it really doesn't become all that cumbersome. So NumPy, numerical Python, is used primarily for doing operations with, we're out of time, aren't we? I always forget. Right? We're done at 10 of, yeah? Okay, man, my two classes just can't teach an old dog new tricks. Okay, just let me finish my thought. So NumPy is used for array operations. So entering arrays, vectors and matrices, doing basic operations on them, NumPy. SciPy, which is scientific Python, has all the linear algebra operations in it, has a lot of other things which we'll see throughout the semester. So SciPy, normally we import SciPy as SP. So just like NumPy is NP, that's the standard, everyone does it. So then you have a transpose, you have the determinant, you have the inverse, eigen, and again, rather than typing out SciPy, I can just have sp.linalg, or I can even get rid of this if I want. But I, look in the tutorial for examples of that, how it's used. One thing that's a little goofy is if you want if you want I, the complex number, square root of -1, guess what? It's J. Does anybody know why it's J? Why did they choose J instead of I? Huh? It kind of looks like an I, but why wouldn't you just use an I? So someone said, is I taken? Yes. So for whom is I taken already? Huh? Not well. Okay. Well, we'll use I for increment, but in a math context, not a programming context. Think Tuesday. What did we use I for on Tuesday? It was the current. So electrical engineers, I is taken. It's the current. So when they have a square root of -1, the imaginary number, they use J. So it just so happened, so this is what you get for this ecosystem. It just so happened that whoever developed the C math package happened to be an electrical engineer. So they got to decide, and they chose J is going to be square root of -1. Deal with it, non-electrical engineers, not a big deal. All right, so we'll talk more about Python next time, as well as I'll show you how to do a number of these linear algebra operations in the 3, really the 2, and we'll pick that up. And then I'll be giving you, so you get ready for problem set 1 will be coming next week. And between now and then, really start thinking about and looking into more in depth the Python versus MATLAB question. Feel free to use Slack to, quaternions. Oh, don't get me started on quaternions. So Slack is a great, use that for discussing. What are you guys using and why? If you're using MATLAB, blah, blah, blah. Are you using the VCL? Do you have it on your computer? If you're going to use Python, are you using Anaconda, or you like something else? Spider versus, start those discussions on Slack and get them going, and that'll be helpful to all of you to help you make those decisions. So between now and Tuesday, really start thinking about which you're going to decide to use. All right, so I will see you Tuesday. Have a good weekend.